Hello everybody, Justin Miller, Arts and College Physics. We're here to do a nice little problem involving some double slit interference patterns. So here's the problem. We've got ourselves a slit separation of 2.5 times 10 to the negative 4 meters, or 0.25 millimeters if you want. We've got a single wavelength of light, 560 nanometers, that is shining upon those two slits right there. We've got a screen that is 1.50 meters away from the slits, and we get this interference pattern. And we're asked specific things about, hey, what's the angular separation between the first and the second order maxima, and asked a bunch of stuff, as was noted. So let us just get started with this and look at what is the angular separation between the first and the second order maxima. All right, so let's grab a pen here. Got my calculator, that's great. And you'll be able to see the problem. All set. So first and second order maxima. So we can go ahead and go over to part A here. And drawing all this out gets really messy really quick. But ultimately, we've got ourselves some angle between, I guess we kind of got to draw out, between where the first order maxima and, try to draw this cleanly. There's the first order maxima right there. This whoosh. And then we've got the second order maxima right there. We want to know, what is that angular separation between these two? We're asked in part A, this delta theta. Call it delta theta 2-1, just to name it something. Now, what is that angular separation? So, what do we need to figure out? If we figure out what theta M1 is, theta B1 is, and what theta B2 is, we can take the difference between them and get ourselves what that theta 2-1 is. So, theta 2-1, delta theta 2-1 is going to be equal to theta B2 minus theta B1, again, because we're talking about maxima here, second order maxima and first order maxima, the angular separation between them. So, if you wanted to put a little b here too, that would be fine, but we've got it noted there. All right, so what do we need to find then? Well, we need to find these thetas, theta B2, theta B1, and then we're in good shape here. So we got in general, again, that d times the sine of theta is equal to m lambda for a maxima. And well, we've got two different thetas here. So what do we have? Two different thetas, two different m values. We can solve this out for theta pretty easily. Divide both sides by d, take the arc sine, and we've got that theta is going to be equal to the arc sine of m lambda over d in general. And then we can go ahead and throw in our particular thetas that we want. So we're going to get ourselves theta B2 is going to be equal to arc sine of 2, m is equal to 2, times lambda. Lambda is 560 nanometers. So we got 560 times 10 to the negative 9 meters. Want to be consistent with units here. We've got lambda generally given in nanometers. The slit separation is generally given in millimeters or meters. Have to make sure we're utilizing the same units. So I just stick everything in meters in this case. Write this as 2.5 times 10 to the negative 4 meters. So meters divided by meters gives us meters. Gives us something unitless. And that's what we want. So if anything, be careful with the units there. Because a lot of times I do see people just going, oh, it's just 560 divided by 2.5. And that is wrong. So anyway, we're going to do the angles in degrees. So we're going to stick with degrees. Yep, I'm in degrees. That is grand. And we got ourselves arc sine 2 times 560 e to the negative 9 divided by 2.5 e to the negative 4 gives us an angular separation, angular separation between the central maxima, or the principal axis, and the second order maxima as being 0.2566, we'll just call it 9. 0.25669 degrees. Hey, that's a really small angle, right? Well, that's right. These are making really small angles relative to the principal axis, which ultimately sort of justified us saying that they're parallel to one another, because one slit's right here and one slit's right here. What's going to be the true difference? Not much. Very, very, very small. So this is just the angle at which this occurs at. Anyways, we got ourselves theta b2. We're going to do the same thing for theta b1. We've got that it is the arc sine of, well, n is going to be equal to 1, multiplied by 560 times 10 to the negative 9 meters, divided by 2.5 times 10 to the negative 4 meters. And that is going to give us, so we'll switcheroo right here, turn that to 1, and we got ourselves 0.12834 degrees. So what do we do with those? Well, we take the difference between them. That's it. Delta theta, 2,1, is going to be this minus that. Don't bother writing that down. We've got 0.25669 minus answer. Gives me, that looks familiar, 0.1283. Which comes out to 835. Anything but. This is slightly rounded. These values are rounded a little bit. Notice something. The angular separation between the first order and the second order is right about the same angle that the first order makes. So going from the principal axis to the first one is about 0.12834 degrees, and going from the first one to the second one is an additional 0.12834 degrees. And it turns out to play out like that as we go up to the next one. Again, it's about 0.12834, because these are really small angles here. And you end up getting something that behaves fairly linearly because everything's so packed together. Really small angles, recall, this number is going to be really small. We have that the sine of small angles is approximately the angle itself. So you will find some books that they just kind of take this arc sine away and just use this. That ends up being in radians, however. But just using that and calling it a day from there. I prefer not to do that because there's cases where you start exceeding small angle approximations, and then that invalidates being able to just say the sine of theta is equal to theta. So I just recommend sticking with this. It's the arc sine of n lambda over d, and we're all good. So we've got ourselves that. What else can we ask? We can ask, what is the spatial separation between the first order maxima and the second order maxima? We can look at this. Delta y 2,1. What distance is the first and second order maxima separated by? All right. So throw that out up there for a second. We can say B. We want delta y 2,1. Well, that's going to be equal to yb2 minus yb1. And y in general, the distance measured from the principal axis, or the central maxima, is just equal to L times the tangent of theta. So we can go ahead and say, well, yb2 is equal to L times the tangent of theta b2, which is then equal to 1.5 meters times the tangent of theta b2, which was 0.25669. 0.25669 degrees. And we get a number for that. And we got that yb1 is equal to L times the tangent of theta b1, which is 1.5 meters, times the tangent, messy, sloppy, tangent of 0.12834. 0.12834 degrees. Equals. Let's just go ahead and do this. So I've got 1.5 times the tangent of this gives me 0.00336. This one, 0.00336 meters, or 3.36 millimeters. That would be fine. Well, let's calculate what this one is and see what that is. I'll just go ahead and stick it in 1.5. It's the tangent of 0.25669. And we've got 0.00672. Or 6.72 millimeters. Let's look at the difference between these. Delta y 21 is going to be equal to this minus this. Well, look at this. This is exactly 2 times this. So what's half going to be? That's right, 0.00336 meters, or 3.36 millimeters. There is the spatial separation between the first and the second, which is the same as the spatial separation between the principal axis and the first order maxima. And we'll find that from the second to the third is approximately 3.36. From the third to the fourth, 3.36. Fourth to the fifth, 3.36. And there we go. That's basically that packed together really, really tightly. All right, so that was the next question here. Next question is, what is the angular separation between the second order and the third order, and what distances are they separated by? So if we did it for 1 and 2, do it for 2 and 3, just to show that we get the same numeric values. So I'm just going to go ahead and throw this over here. In part C and D are asking basically the same thing for now. Theta B2 and theta B3. We want delta theta, see delta theta 3,2. It's going to be theta B3 minus theta B2. We already know what theta B2 is, no need to calculate that again. All we need is theta B3. Theta B3 is the arc sine of m lambda over d. M is equal to 3 times 560, oops. 560 times 10 to the negative 9 meters divided by 2.5 times 10 to the negative 4 meters gives us, let's calculate that on out right here. Sine 3 times 560. We've got 0.38503. 0.38503 degrees. Well, what is 0.25669 plus 0.12834? That's right, 0.38503. So, kind of the same thing, which we can ultimately see by getting this delta theta 3,2 now being equal to, I'll put it in my calculator, I got that number there, minus the 0.25669. And, oh my gosh, 0.12834. So there we go. The same angular separation between the successive maxima. That's it. You get nice well-behaved sort of linear behavior there. Part D, we are looking at now the delta y 3,2. What is the linear separation between them? Well, that is going to be equal to yb3 minus yb2. We already know what yb2 is. It's right there. 6.72 millimeters. So let's just get yb3. yb3 is equal to L times the tangent of theta b3. Theta b3s are right here. So let's calculate that. 1.5 times the tangent of 0.38503, and we get 1.008, 1.008 10 to the negative 2. 1.008 times 10 to the negative 2 meters, or 10.08 millimeters. That'd be fine too. So what do we get? Well, if we're looking between 3 and 2, we've got 10.08 millimeters minus 6.72 millimeters. Let me just go ahead and put that in. We've got the answer, minus 0.00672. And I get 0.0336. Delta y32 is going to be our 0.01008 meters minus 0.00672, which is then equal to 0.00336 meters, 0.36 millimeters. Again, we get the same spatial separation between successive maxima. So no big surprise there, just really demonstrating, showing mathematically that's how this all works out. A couple more parts here just to make this touching on everything. What angles do the 0th, 1st, and 2nd order minima occur at, and at what locations on the screen do they appear? So I'm not going to look at the actual separations between them, but we can, excuse me, look at just where they are angularly and linear. So 0th, 1st, and 2nd order minima. So, what do we have for minima? We've got that d times the sine of theta is equal to m plus 1/2 times lambda. That's it for minima. That's what we're looking at, so that's what we want to use. We'll go ahead and solve this out for theta. Theta for minima is equal to arc sine of the quantity of m plus 1/2 times lambda divided by d. So we can stick in an m equals 0, an m equals 1, m equals 2, and figure out different thetas here. Let's just get all these thetas. We've got ourselves that theta 0 dark, 0d is going to be equal to arc sine of, well, lambda is equal to 0, that's just equal to 1/2. 2 can drop down, we got lambda over 2d. Lambda over 2d. We get a number for that. We've got theta 1d is going to be, well, if we stick a 1 here, that's going to be 3/2. We'll have 3 lambda over 2d. Arc sine of 3 lambda over 2d. And then we've got theta 2d. We stick a 2 here, 2 plus 1/2, 5/2. 5 up at the top, 2 down at the bottom. We've got arc sine of 5 lambda over 2d. Excuse me. So what do we got? We know what lambda is, 516 nanometers. We know what d is, 2.5 times 10 to the negative 4 meters. And let's do these really quick here. So we've got arc sine of 560 e to the negative 9. 1 times that. Divided by quantity of 2 times 2.5 e to the negative 4. And we get ourselves, this angle is 0.06417. 0.06417 degrees. That's a pretty small angle, right? So that's to the 0th order maxima. Where's the 0th order maxima? This is the 0th order maxima, right? Excuse me, minima. 0th order minima, excuse me, sorry about that. That one's right there. 0th order minima. It's the first one above the principal axis. First one is the 0th. Be careful of that. Because if you ask for the first one is m equals 1. The first one is m equals 0. There we go. There's the first one. Here's the second order. Excuse me, the second one, which is the first order. So let's do this. Here's the 0th order, first order. Here is the second order there. We're looking at, ultimately, that angle right there. That's our theta 0d. That's a pretty small angle, 0.06417. Look at what the angle for theta 1b was. What did we have? We ultimately had that it was 0.12834 degrees, which is 2 times that. So you go up half the angle, you're at the 0th order minima. You go up the other half of that angle, and you're at the 1st order maxima. So there's symmetry. These are exactly angularly halfway in between the successive maxima. But that's just one thing. So let's get these other ones out of the way here. Look at the 1st order. Let's go with this. Change that to 3. 3 times. This is 0.19251 degrees. 2 times this. Add in the other half there. 3 halves. Anyways, we'll go over to this one. 5 now. We got 0.3206. 0.320866. So look at the differences between these. The differences are still equal, not just equal to this any longer. Anyways, once we get that, if we want to know the locations on the screen, we're going to end up finding that they're halfway in between the successive or consecutive maxima. We'll still do it though. We got ourselves that y0 dark is equal to L times the tangent of theta 0 dark. y1 dark is equal to L times the tangent of theta 1 dark. y2 dark is equal to L times the tangent of theta 2 dark. Go ahead and calculate those out really quick. We got thetas, we know that L's 1.5 meters, So 1.5 times the tangent of 0.06417. Good. We get 0. We'll just do it in millimeters. 1.680 minus 2. 1.680 millimeters. This was equivalent to the distance to the first order maxima, and that's halfway in between. 1.68 millimeters to 3.36 millimeters, 1.68. Anyways, we'll go over to the next one, and change our angle to 0.19251. 251 gives us 5.040 millimeters. And to the next one, we added the difference in between them, which would be the 3.26. Go ahead and figure that out. But let's just do this. 3206, 086, 2.86. I saw that. 3206, 8.400. Which would be this plus that, because we got to add a distance between the consecutive maxima. But at any rate, it's the spatial separation. It's always going to be equivalent to the spatial separation of the maximas as well. This follows a little bit of a different pattern. That's it. One last question. Whew. I think it is, what should the distance of the screen be if we actually want the first order and the second order maxima to be separated by exactly 3 centimeters. Right now, we've got them separated by 3.36 millimeters. We want exactly 3 millimeters. Let me make sure that that's what we actually ask here. What I'm asking. Yes, first and second order maxima separated by exactly 3 millimeters. So, what should we note? Well, if the screen's 1.5 meters away, when it's 1.5 meters away, that delta y, 21, that is 3.36 millimeters right now. So if we wanted to drop down to exactly 3 millimeters, it should stand to reason that we have to put the screen a little closer. So, the closer we put it, the smaller the spatial separation. But the angular separation remains the same. That's unchanged. So what do we want? Well, again, we want that y2 bright minus y1 bright is equal to 3 times 10 to the negative 3 meters. 3 millimeters. What's y2 bright minus y1 bright? Let's look at this. This is going to be L times the tangent of theta 2 bright minus L times the tangent of theta 1 bright. We're saying that that has to be equal to 3 times 10 to the negative 3 meters. All right, so what do we get out of this? Well, if we factor L out, divide both sides by what's left over, and we get that L must be equal to 3 times 10 to the negative 3 meters divided by the quantity of the tangent of theta 2 bright minus the tangent of theta 1 bright. There we go. Do we know what theta 2 bright and theta 1 bright are? Yes, we do. They're actually right there. 0.25669. Theta 2 bright, 0.25669 degrees, and theta 1 bright was equal to 0.12834. So we can stick those in there. And we got ourselves an L, excuse me. All right, so let's just do this. 3 divided by the quantity of the tangent of 0.25669 minus the tangent of 0.12834. It's all good there. And we got 1.342 meters. We have to move it closer a little bit, right? A little bit under 16 centimeters closer, but closer nonetheless. Move it closer, we reduce that spatial separation between all of the successive maxima slash minima. That was part F. All right, that's it.